Welcome back, students. We're going to be talking about arithmetic sequences today. So a sequence is just an ordered list of numbers. Each number in the sequence is called a term. And each term, A of n, has a specific position n in the sequence. So in that notation that you can see right there, where we have a and then as a subscript the n is always going to tell us which term number it is. Okay? So right here, the number 5 is the first term, so we would say a of 1. 15 is the third term, so you see how we've written it. And then a of n is just to represent any term out to some number n, where n could be any number. In an arithmetic sequence, the difference between each pair of consecutive terms, consecutive means one after the other, is always going to be the same. So this difference is called a common difference because it's always the same. So the difference between a 10 and a 5, 10 minus 5 is 5. 15 minus 10 is 5. 20 minus 15 is 5. So as I get the difference, as I do the subtraction, I always get the same number, a positive 5. Hence we have a common difference. Each term is found by adding the common difference to the previous term. So now to find the next number after 20, I would just add 5, and it would be 25 next. So let's go ahead and extend some of these sequences. We got negative 7, negative 14, negative 21, negative 28. Now in order to figure out what the common difference is, we need to subtract the numbers going backwards. Okay? So negative 14 minus a negative 7 would give us negative 7. Negative 21 minus a 14 would give us negative 7. Negative 28 minus a negative 21 gives us a negative 7. In other words, we keep on going down by 7. So to find the next number, we minus 7 again and get a negative 35. Minus 7 again, get a negative 42. So the seventh number out is going to be negative 49. Okay, so that's how you extend it. Find the common difference, and then you can keep on adding or subtracting the number depending on whether or not the common difference was positive or negative. So to graph an arithmetic sequence, we make a table and then we plot the ordered pairs using the number of the term for our x and the actual term as our y. Okay, so here we've got an arithmetic sequence. First term, second term, third term, fourth term, going 4, 8, 12, 16. If we find our common difference, 16 minus 12 is 4, 12 minus 8 is 4, 8 minus 4 is 4, so which means we would add 4 to keep on finding the next term. So as I graph these, we graph the 1, 4, 2, 8, 3, 12, and 4, 16. One thing we notice from arithmetic sequences as they are graphed is it's a line. Okay? Arithmetic sequences are linear in their graphs. And because of that, actually the equations look similar to the y equals mx plus b equation for a line that we have learned previously, though with a few adjustments to it. Now the slope of this line is going to be, like we already figured out, a 4. That's how much it's increasing by every time. All right, so now looking at this, we're asking the question, is it an arithmetic sequence? Well, let's think about our numbers, 15, 12, 9, 6. Let's see if we can find a common difference. 6 minus a 9 would be a negative 3. 9 minus 12, negative 3. And 12 minus 15, negative 3. We minused a 3 each time. 15 minus 3 is 12, 12 minus 3 is 9, and on and on. So we do see there is a common difference. Because there's a common difference, then yes, it's going to be arithmetic. It is arithmetic with a common difference of negative 3. We could also see it over here in the graph by the fact that it formed a perfect line. Arithmetic, when graphed, is a line, and that's what we saw. Okay, so now let's talk about the equation for arithmetic sequences. Like I said, it's going to be very similar to y equals mx plus b with a slight change. The slight change is rather than x, we're using this n minus 1. Okay? We still have a of 1, the first term, acting as kind of like our b. It's not going to cross at the y-axis, but it is our starting point. And d is exactly the slope. D is the slope. That's all there is to it. So here's our m. X has changed n minus 1. And we have, rather than b, we're talking about the first term. Okay? Now there's a reason why it looks like this, and it's because finding this equation from an already given sequence actually flows very nicely. So let's talk about how that works. We want to write an equation for the nth term of this sequence. All right, so our first term is a of 1, and our common difference here was a negative 3. It was always going down by 3. Now, let's just imagine we were trying to find, this is asking for us to find 50, but before we get to finding 50, let's quickly talk about how we would find even the fifth number here. Okay, so in order to find the fifth number along this, I would start at 14, and then I would minus 3, 1, 2, 3, 4 times. So notice to get to the fifth number, I had to minus 3 4 times. So now let's go ahead and look at how those things create our equation. So replacing a1 with our first term of 14 and our common difference with a minus 3, we get this equation. 14 minusing 3, n minus 1 times. Well, remember, to get to the fifth one, I had to minus 3 4 times. Okay, and the same will always be true. In order for us to reach out to that 50, I am going to have to minus 50 49 times. Now, what I'm also showing right here with this simplifying step is to show, notice it can be changed into y equals mx plus b. So yeah, we had a slope of negative 3. Our y-intercept would have been at 17. These are the same equation. However, when you're given a sequence, many times it's easier just to write it like that. You have your starting number, then you're subtracting something, n minus 1 times. Okay, so if we want to find the 50th term out, we can use our equation and do negative 3 times 50 plus 17. And we get negative 133. All right, so online bidding for a purse increases by $5 for each bid after the initial $60 bid. So we want to write a function that's going to represent this arithmetic sequence. We know it's an arithmetic sequence because it keeps on increasing by the exact same amount. Okay, so we'll have a common difference. Two things we need to figure out are the first term, so they say the initial bit is 60, and what the common difference is, 5. It keeps on going up by 5. There it is. We've got our arithmetic sequence. We're starting at 60, we're going up by 5, and we go up by 5 n minus 1 times. We can simplify this to our linear equation, y equals mx plus b, by just multiplying through and then combining like terms. If we want to graph that function, here we've got the numbers in order. Notice that we started with 60, then the bid went up to 65, 70, 75, and on and on. Okay, we notice that once again, it did form a perfect line. Now, here's another question. The winning bid is 105. How many bids were there? Now, there's different approaches we could take in solving this. Some may be easier than others. Notice we could continue this table out and just keep on going and keep on counting out. That might take a bit of space, but we would eventually get there. But I also want you to think of, what if it was a much higher number? What if the winning bid had turned out to be $500? Think of how far you'd have to continue that table counting by fives to finally get there. That might be far more of a challenge. So the other way we can approach this is by using our equation. A of n is supposed to represent the value of the term. They just gave us the value of the term, 105. We want to figure out how far out is it, what n value or which bid number is going to give us that bid amount. Well, this equation should tell us. All we need to do is change A of n to 150, and then we can solve for which term number would give us that. So minus 55 from both sides, and we get 5n is equal to 135. Divide by 5. So the 27th term. Okay, so to make it all the way out to 105, we would have to make it out to the 27th term in order to find that. So there were 27 bids in all. Okay, I hope this helps you with your work with arithmetic sequences.